You made it. It's the second topic of HSC, electromagnetism, and we are looking at the interaction between charged particles and uniform electric fields, and particularly comparing how that, um, looking at how that compares with projectiles in gravitational fields. So the first thing is to look at projectiles in gravitational fields. So if we imagine a gravitational field, a bunch of down arrows pointing towards Earth, we have a projectile moving through it. So some projectile above the Earth, it's going to have some gravitational potential energy just by being held above the Earth. If it was thrown to the side, it's going to fall down and plonk in a half parabola sort of motion. That motion is going to be dictated by the equations, the projectile motion equations, which are in here, boom, boom, and boom. Now, a mass in a gravitational field, it works the same as a charge in an electric field. So if we change this to an electric field, so the bottom of this just needs to become a charged plate, it would be going towards a negative plate and it'd be coming out of a positive plate. Boom, 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 boom. In this case, everything will work just the same. Instead of U, we would call it W, the amount of work done on the ball to bring it up to this place, or the amount of work sort of done as it falls down. And instead of the ball having mass, the ball would have charge, and it would be charge that is pulling it through this electric field rather than mass pulling it through a gravitational field. So if you replace gravity with electric field, you replace mass with charge, you end up with the same kind of thing. And it still is a mass, it still obeys Newton's laws. We're just using a different type of field. And actually it works the same if you have magnets in magnetic fields. So mass in gravitational, charge in electric, magnets in magnetic fields, they work the same way. So let's go through a problem to see this happening in action. We're going to have a similar setup. Um, let's do it in this color, where we have charged parallel plates. And charged parallel plates is how you end up with uniform electric fields. So we'll have our positive plate up here. Yep, just pretend there's positives all the way along there. Our negative plate down here. Negative, giving us a uniform electric field. Uniform just means the electric field is the same the whole way through. This stops it from getting very confusing if we have a changing electric field. On the edges, it is going to curve outwards, so we're not dealing with things that are happening in the edges. And let's just say we have a positive charge. Actually, let's make it a negative charge for fun. Let's say it's got a charge of 2 coulombs and needs a mass as well. It's not an electron. It's a big metal ball that's 3 kilograms heavy and has a charge of 2 coulombs. Okay, and let's just pretend that this is not in any kind of gravitational field. This is floating out in space, something like that. Now this whole setup is attached to a power source of 11 volts. 11 volts, and the distance between the top and the bottom is 2 meters. Now I've given you a fair bit of information, but I'm going to ask you for something novel. I'm going to ask, when you let go, where is it going and what velocity does it have by the time it finishes moving? So it's a negative charge. It's going to be repelled by the negatives down here, attracted to the positives up here. So it's going to make its way all the way to the top, boom, crash, and it's going to have some velocity. Question is, what will that velocity be? And if we have a look at our equations up here, the only one with any kind of velocity is this kinetic energy equation. Okay, to work out the amount of kinetic energy it has, we need to work out how much work it took to put it in that place to begin with. Work needs QED. We've got Q. We don't have E though. We've got distance. So we need to work out we need to work out E. To work out E, we're going to need to use this equation up here. So there's quite a multi-step process here. So we start up here getting E. Let's do it in blue. So E is equal to V over D. It's going to be a lot of fiddling around here. E is equal to V over D, and that's going to be 11 volts over a distance of 2. 11 divided by 2 is 5.5. That is coulombs per Newton. Yep, believe me, that's what I've written. Okay, now from that we need to work out the amount of work on it. So we can use either of these. Let's just use the first one. Work is equal to the QV, which gives us the charge we've written is 2. V we've said is 11. So 2 times 11 is 22. 22 joules of work. Actually, I just realized we didn't need to use this top equation at all. I'll show you later why we will get back to that equation. We will use it. So we've got the work. Now 22 joules of work, that's kind of like the gravitational potential energy. When we let go, all of that's going to turn into kinetic by the time it's moved those 2 meters. So it's going to move 2 meters, crash, and then by that time, these 22 joules would have all turned to kinetic. So that kinetic energy, using this equation here, if we rearrange that for velocity, we end up with velocity is equal to K, kinetic energy, doubled, because we can get rid of this half by doubling K, so 2K over mass. If we divide mass onto that side, we get mass there. And I've drawn this too small because to get rid of this squared, we're going to have to square root this side here. Square root of 2K over M, get my calculator, 2K over M, we get about 3.8 meters per second. All right, now just to show you how interconnected all of these equations are, I'm going to try and get the same value in a different way using this electric field strength we've got here and the other 2 equations. So with this electric field strength, we can actually work out the force on the charge. So the amount of force on the charge is going to be equal to Q times E. And Q is 2, E is 5, 55? No, 5.5. There's supposed to be a point in there. Okay, so 2 times 5.5, that's going to be 11 newtons of force. Yeah, now we can do something with this. With this 11 newtons of force, we can actually work out what the acceleration is. We've got the force, we've got the mass. So F equals ma, we can work out that A is going to be equal to F on m, which is 11 divided by mass of 3. 11 divided by 3 is 3.7. 3.7, and that's meters per second per second. Now, what on earth am I going to do with this acceleration? Well, this is essentially a projectile. It's falling up instead of falling down because it's got negative charge, kind of like negative mass moving against gravity rather than with it. And so because it's accelerating up, it started at rest, we can actually use our projectile motion equations to sort this out. We have a starting velocity, we don't have a time, so this is our equation that doesn't use time. We know that the initial velocity here is 0. Acceleration we just calculated. The displacement is the 2 meters it's traveling through, so we can use that to work out V. So it's going to be V is equal to that 0, cancel that, get rid of that square, so it's going to be square root of 2as. V is equal to the square root of 2as. That's 2 times 3.7 times 2 meters, and that comes to a lovely 3.8 meters per second. Same as what we got with the other method. So, yes, we're doing a new topic, electromagnetism. However, really nothing has changed. We're still using the projectile motion equations. We're still using Newton's laws. The only difference is we've swapped out gravitational fields for electric fields. We swapped out mass for charge. That's all. Look forward to doing more next time.